In the previous video, I said we were going to learn how to show that many languages are not regular. So let's begin by looking at one of the languages we mentioned, which was the language of strings which have equal numbers of A's and B's, with the A's preceding the B's. And the way we're going to proceed is we're going to suppose for a contradiction that actually L is a regular language, which means that there's a DFA M that recognizes L. So let's suppose L were accepted by some DFA M. And given a machine, we can ask how many states it has. So let P be the number of states in machine N. And now let's consider a particular input. Let's look at the input, which we'll call S, which consists of PAs followed by PBs. And of course, this is in the language L. Now what we're going to do is we're going to look at the sequence of states that M goes through on reading this string. And so we begin at the start state, of course, let's call that Q0. And we read a sequence of A's, and let's just call the states we go through Q1, Q2, and so on and so forth. So eventually we've read the first PAs, and we've reached some state, call it QP. And now we keep going and we read the Bs. And eventually we read PBs, and let's call the state we've reached at that point Q2P. And the important point, of course, is as this string is in the language, we reach an accepting state. Now, this machine, by assumption, has only P states. That means there's got to be a lot of repetitions in this sequence of states. And in particular, there's a repetition in going from Q0 to Q1 to QP. This is a total of P plus 1 states that we've gone through, but there are only P different states, and therefore there must be a repetition by the time we've got to QP. Let me write that down as it's important. Must be a repetition at or before . And let one such repetition occur. So let one repetition occur at Qi and Qj. What I mean by this is that Qi and Qj are actually the same state, but we have J comes later than I in this sequence, and furthermore, P is greater than or equal to J. So Qi occurs somewhere here, Qj occurs somewhere here. Now I'm going to redraw this picture to emphasize the pieces that we have. So we start at Q0. At some point we get to Qi, which is where we have the repetition, and we end, of course, at Q2P. And Qi is the same state as Qj. So now looking at the sequence of states we go through and viewing this as a graph, we are going to read some I repetitions of A in going from Q0 to Qi. Then we're going to read a further J minus I A's in going from Qi to Qj. so that by the time we've reached qj, we've read a total of j a's, and then we read the rest of the string in going to the final vertex q2p. So this is another p minus j a's followed by p b's. And let me just give some names to these pieces of the string. I'll call the initial I a's x. I will call the following j minus I a's y, and I will call the remainder of the string z. So my string a to the p, b to the p can also be written as a concatenation of x, y, z. And x, y, z is an L. Now, this picture, this graph, shows a set of paths that exist in our finite automata. So let me ask, what happens if I read the input string x, y, y, z? Well, if I read x, this is the DFA, it's going to take me from Q0 to Qi. Then in reading y, I go from Qi round this loop back to Qj. If I read y a second time, I go round this loop a second time. And then when I read z, that takes me from Qi or Qj, it's the same state after all, to this accepting state Q2p. And that means that x, y, y, z is also in my language L. But what is x, y, y, z? X, y, y, z is a to the I, a to the j minus I, a to the j minus I again, and then a to the p minus j, that is p minus ja's, followed by p b's. Let's just add up the number of a's that we have. And what you see is we have p plus j minus I a's. And the important point to remember from a minute ago is that j is greater than I. So the number of a's and the number of b's in x, y, y, z are not equal. There are more a's than b's. But that means that in fact, x, y, y, z is not in the language L, because the language L consists of those strings with equal numbers of a's and b's, with the b's following the a's. So we've managed to deduce that this string is in the language L, and also that it isn't in the language L. That's a contradiction. And what was our assumption? If we look back at the previous slide, what we see is we assumed that L was accepted by some DFA M. And so that assumption must be incorrect. So we can conclude, our conclusion is that L is not accepted by any DFA. In other words, L is not regular. Okay, so let me summarize what was going on. The key to our argument was to show that we had a string and the path that it caused us to follow in the DFA has a loop in it. And if we label these three pieces of the path by the strings that cause us to traverse them, namely x, y, and z, then what we know is that both x, y, z and x, y, y, z are accepted. And That's what is going to give us a contradiction. And one way to look at this is a DFA is really a directed graph. And in order to accept a string, you follow a path from the start vertex to an accepting vertex or accepting or final vertex. And if the string is long, the path that you're following has to be equally long. And in a finite graph, eventually you're going to get to strings whose lengths force the corresponding path to have a cycle. And once you've got a cycle, you can get a repetition of the form that we've just shown here. And that then allows you, in cases that the language is not regular, to pull out a contradiction.